Dear students, welcome to Digital System Design using Verilog class. Today we will be discussing the topics from fourth module. It is I/O interfacing. Right. So the topics in these modules are I/O devices, I/O controllers, parallel buses, serial transmission, and I/O software. So now we will be discussing about I/O devices. Especially we will be concentrating on input devices now. So coming to the introduction of this I/O controllers or I/O devices, input output controllers which can connect the system, okay, and they are able to sense and affect the real world physical properties. That is what I/O devices are used for. So there are multiple devices or multiple range of devices available which are used in the embedded system, so that can be accessed by embedded processor. So once we connect that input device or an output device, it has to be accessed by the embedded processor as well as by the embedded software. So we are going to understand that process. Once we connect the I/O devices, it should be accessed by the embedded processor as well as there should be a support from the embedded software to get the readings. So coming to the I/O devices as well as the transducers. Basically the transducer converts real world signals like temperature, humidity, pressure and all. Transducers convert one form of energy to another form. Okay, so some of the examples in like microphones, loudspeakers, thermometers, positions, pressure sensors, all this comes under transducers. Okay, when we talk about input transducers, sensors will act as input transducers. Basically sensors is going to convert physical quantity, any of this physical quantity, to an electrical signal. That is what sensors will do, and those sensors will make use of analog to digital converters. Coming to the output transducers or output devices, there are called actuators. It may be a solenoid valve, or it may be a pneumatic valve, pneumatic cylinders, hydraulic cylinders. All those things comes under actuator. They may require to convert that signal from digital to analog, vice versa. At the input side, you can see that analog signal like temperature has to be converted to digital form. That's why ADC is made use. At the output side, the same digital signal again it has to be converted back to analog form by the help of DAC. Okay, so there are many other human interface devices are also available where we'll make use of buttons, switches, knobs, keypads, mouse, LED indicators or LCD indicators, displays, speakers. Multiple type of other devices can also be connected, which comes under input output devices. So you can have a look at this keypads and keyboards. There are two ways. Push button type keypad is provided here, where an input register is also there as well as the output register. Depending on the key pressed, certain binary value will be selected and it is given to the output register. Similarly, we have debouncing switches available over here. You can see that a recall switch, debouncing type of switches are provided over here. These are the input devices to the system. And input can also be provided by the knobs as well as by the position encoders. Okay, knob, you can just recall a potentiometer where we will rotate the like a variable resistor. When we rotate, the resistance changes. That is a perfect example of a knob, the way in which we will give the input. So in digital circuits, it could be a push buttons. For example, we will use a button in the systems like MP3 players and all, where for volume up and down. Okay, position encoders is like depending on in what position that particular knob is, certain operation will be selected. You can just think of a fan regulator. Okay, so if it is in position 1, the speed of the fan is less. When the position is 2, the speed increases. Like that, position encoders are also there to provide the inputs to the system. Likewise, incremental encoder, you can see that if absolute position is not important, we will make use of incremental encoders. That is nothing but simply rotating the knob. It is possible for us to change the brightness of the bulb like that. Counterclockwise, like an anti-clockwise direction, and this is clockwise direction, where we can control the speed, intensity like that with the incremental encoders. So analog inputs is nothing but basically the real world signal what we get will be in the form of continuous wave, that is analog in nature. So microphones will make use voice signal has to get converted into electrical signal. So microphones will be made use in phone, camera, voice recorders and all. Accelerometers are also required in airbag controllers. Fluid flow sensors in most of the industrial applications, there are fluid flow sensors. Gas detectors in home automation and safety, we will make use of gas detectors. Okay. Coming to analog to digital converters, what is the purpose of analog to digital is nothing but, as I already said, the real world signals are analog in nature. If you take an example of temperature, the sensors usually sense the temperature and provide the output in the form of analog. We need to convert that into digital, so we'll take the help of ADCs. Okay, so it is nothing but the basic component or element used here is analog comparator. Okay, so analog comparator is nothing but we have made use of op amp. Okay, and with the input voltage and the reference voltage, we will be converting that analog voltage into digital signal. So resolution is nothing but what is the output number of bits we require, that defines the resolution of this ADC. Okay, so in the ADC you can see there is an encoder, op amp, a series of resistors are connected, input voltage, reference voltage is made use. Let us understand one type of ADC, that is successive approximation type ADC. Okay, so again this is a device which is going to help us for processing the real world data or signal into digital signal, conversion of that. Okay, real world signals will be like temperature, humidity, pressure, right? So all this comes under real world signal. So there are many types of ADCs are there. In that successive approximation is one such type, successive approximation ADC, where it is one of the low cost medium to high resolution application will be satisfied by this ADC, right? So usually the resolution for successive approximation ADCs is around 8 to 18 bits. Okay, likewise you can have a look at that. SAR followed by DAC has been connected over there. Successive approximation type ADC, okay, the signal can be converted to again a digital to analog conversion can be done over there. Okay, so it consists of a comparator, right? Signal comparison has to be done, analog input, analog voltage reference, start signal, clock has been provided over there. So it consists of a comparator, digital to analog converter, successive approximation resistor, okay, along with the control circuit, right? So these three are the major units: digital to analog converter, successive approximation resistor, okay, op amp or control circuit, right? So input sample, the sampled input, suppose if you are providing 5.8 volt, the reference of the ADC is around 10 volts. So when the conversion starts, the successive approximation resistor is going to set most significant bit, that is MSB, to 1. Okay, it is going to set the MSB to 1 and other bits to become 0. Likewise what you can see over there, right? So that means 1,000, that means 10 volt as a reference voltage. It is going to produce 5 volts, which is half of the reference voltage. So it has to be compared with the input voltage, and based on the comparator output, successive approximation resistor output is dependent. Okay, so if the Vin is greater than the DAC voltage, if Vin is greater than DAC voltage, the most significant will stay as it is, MSB is unchanged. Okay, and the next bit will be set for new comparison. Otherwise, if the input voltage is Vin is less than the DAC value, the most significant bit is set to 0, and the next values will be set to 1 for new comparison. Okay, that is what you are seeing over here. So comparator value gives D7 1 if Vn is higher than the reference value, 0 otherwise. So for next approximation it considers, and the comparator output will be considered from D6, right? So that's how the successive approximation ADC works. Let us discuss this in detail in the regular class. Okay, LEDs are indicators. We'll make use of LEDs also. Okay, single LED shows a 1-bit state, on or off, busy or ready, error or okay. So this kind of signal or information we will get from the device. Okay, so you have seen LEDs in many devices which we are using in our daily life. Okay, there is a calculation also based on this. Determine the resistance from an LED pull-up resistor connected to a 3.3 volt supply. LED has been forward biased, voltage drop is around 1.9 volts. If it is sufficiently bright with a current of 2 milliamperes, okay, so we need to identify the resistance. So assuming the output driver low voltage is close to 0 volt, okay, a voltage drop of the resistor will be 3.3 minus, that is a supply, minus the drop. 3.3 minus 1.9 will be, the remaining voltage is 1.5. So we can make use of Ohm's law to identify the resistance. So it is the voltage 1.4 volt divided by 2 milliamperes of current that is flowing over there. So the resistance of an LED is around 700 ohms. Okay, so the closest standard value available here is 680 ohms. Okay, right. And also there are 7-segment LEDs available. 7-segment LED displays are available, right? So you can, we have already discussed in other modules also, right? So each and every segment is having a control based on what values we send. Certain numbers or digits or alphabets will be displayed using the 7-segment LEDs. Okay, so that is about the input devices as well as output indication. So in the next class we will be seeing output devices which are available, as well as how the DAC works. Okay.